I welcome you all in today's session. As we have discussed the bases and dimensions in the previous session, and we have seen some of the examples. Let's discuss it once more here. That if we have given any vector space V or F, a basis which we call denoted by B is nothing. It is the set of linearly independent set of the vectors v1, v2, so on up to vn. This is the subset of v over f, and these vectors should be linearly independent in v, and this b spans whole of the vector space. That is, span of b is whole of your vector space f, and v1, v2, so on vn are linearly independent. Then we see that this B is the basis. It means that every vector of V can be written as the linear combination of these vectors. So that's V1 so on up to Vn, and the number of the elements in the B is called the dimension of the vector space. Okay, and we are denoting the dimension in this way, dimension of V. So that is the cardinality of the B. Okay, for example, if we have the set S is equal to E1, E2, E3. So here these are the vectors. So E1 is a vector 1, 0, 0. E2 is a vector 0, 1, 0. E3 is a vector 0, 0, 1. And we have to check that this S is the basis for the R3 over R. What we will do, we have to check the linearly independent, whether these sets are linearly independent or not, and whether it spans it or not. So as you know, if you can create the 3 cross 3 matrix 1, 0, 0, this is your E1, 0, 1, 0, this is your E2, 0, 0, 1, this is your E3, and you know this is a matrix A, for example, and it is an identity matrix. It is determinant is non-zero, so these vectors are linearly independent. Also, let's check whether what is its span. So span of S is nothing, that is A1 E1 plus A2 E2 plus A3 E3. So these AIs are the real numbers from the field. So if you will write it, it will be nothing. It will be A1 comma 0, 0 plus 0 A2 comma 0 plus 0, 0 A3, such that these A1, A2, A3 are the real numbers. So you will get a set A1, A2, A3, and these AIs are the real numbers. So it is the same as a definition of R3. So it is giving you the whole real R3 space. So it means that it spans your vector space and it is linearly dependent. It means that S is the basis. So for the basis, we have the two conditions. It should be linearly independent and it spans whole of your vector space. Okay. So these are called, this E1, E2, E3 are called the standard basis. For example, for the R, the standard basis you can write E1 is, for example, 1. For the R2, your standard basis E1 is 1 comma 0 and E2 is equal to 0 comma 1. For the R3, as you have seen, your E1 is equal to 1, 0, 0. E2 is equal to 0, 1, 0. Your E3 is equal to 0, 0, 1. So this is the basis for R3. So the dimension of R1, R is 1. Dimension of R2, that is 2. Dimension of R3, that is 3. Even dimension of Rn is equal to n. Okay, so these are some standard bases. So we are writing in this way. So in this way, we can say if S is equal to E1, E2, so on up to En, so this makes a basis for the Rn over R, so n dimensional. Okay. Similarly, we have seen in the last lecture, if we have M2 cross 2 matrix over the field R, we have the set of elements of this as 1 0 0 0. We have another matrix 0 1 0 0, another matrix 0 0 1 0, another matrix 0 0 0 1, and these four matrices will span this whole set. So let it will be your B. So the linear span of this B is your M2 cross 2 over R, and we have seen that these are linearly independent. So go through the last video, and this is the basis for this. Okay. So you have some properties we have here, that a vector space, a vector space which is not finitely generated is called infinite dimensional vector space. Okay, vector space. So if you do not get the finite set of vectors which will generate, which spans this whole of the vector space, you will see it is it is infinite dimensional. Okay. Similarly, if you have the bases B1, B2 are the two bases for any vector space V over F, then cardinality of B1 is equal to cardinality of B2. Means you have the infinite basis for a vector space V, but every basis should have the same number of elements, and that number of elements is called the dimension of V. Okay. Also, you have to remember that the basis 0 will never belong to the basis. If 0 will belong in the basis, it will become linearly. If 0 belongs to B, then it will become linearly dependent, but by the definition of basis, B is linearly independent, so it means that 0 never belongs in the basis. Okay. Another property, that the vector span, for example, if you will take the 0 vector only, if it is your S, then the span of this S means the 0 vector is only the vector space that is 0 dimensional vector space. So that is only 0. So that is alpha times 0, it will give you the 0. So we have seen the dimension of R2, dimension of yeah, you can check it here also. Dimension of R, as I told, it is 1. Dimension of R2, as I told, it is 2. Similarly, dimension of C but over R is equal to 2, and dimension of C where the field is also C is equal to 1. Okay, remember this. Okay, so similarly, the dimension of M n cross n matrices over the field R is the n square matrix. Okay, if these matrices are symmetric, means for example, if you will take the 2 cross 2 matrix which is symmetric, so if 2 cross 2 A B C D, so we have the 4 independent entries, so that means it has a dimension 4. But if you have A, B, B and it is C, so now you check, you have one entry, you have to get another entry. So if you will get this entry, so you can generate it this as well. So you need the 3, so the here the dimension is 3 for the symmetric matrix. So if you have M n cross n over R as a symmetric matrix, so how many independent entries you require? That is the n into n plus 1 divided by 2. Okay, in general. Okay. Similarly, for example, if you will face this question that the given vectors are 3, let's say v1 is 3 0 2, v2 is 7 0 9, v3 is 4 1 2. These are the given vectors, okay, and you have to show it is a basis for R3 over R. You have to check this is a basis, that this is the set B. You have to check it is a basis. What will you do? You have to check it is linearly independent. So for the linearly independent, make these matrices. Since you have the 3 matrices, so it means you can create the 3 cross 3 matrix. Okay, so you can also check the span as well. So for the 3 cross 3 matrix, so take the matrix A to be 3 0 2 7 0 9 4 1 2, is it? So if you will check, the determinant of A is not equal to 0. So it means that these vectors, so B is the set of linearly independent vectors. So first condition holds. So now by the second condition you have to check the linear span of B. The linear span of B is nothing, that is alpha 1, the first v1, is it? The linear span set of all the linear combinations. So alpha v1, beta v2, gamma v3, or alpha 1, alpha 2, alpha 3. You can write alpha 1, alpha 2, alpha 3, and these alpha are from the real line. Okay, so now put the values. So you will get alpha 1 3 0 2 is your first vector, is it? 3 0 2 7 0 9 is your second. So alpha 2 7 0 9, okay, and your third is 4 1 2, okay, and plus alpha 3 4 1 2, and these alpha is from the real line R. So what does it mean? So you will get the vector 3 alpha 1 plus 7 alpha 2 plus 4 alpha 3. You will get alpha 3, you will get 2 alpha 1 plus 9 alpha 2 plus 2 alpha 3, is it? So these alpha are from the real line. Since these alphas are the real line, so it means that this will be the real number, this is a real number, this is a real number, and with respect to it, you have seen that these are linearly independent. So it means that the dimension of this V is equal to 3, is it? And this linear span is also the dimension 3, because all the 3 vectors are linearly independent. So it means that it spans whole of your vector space. So this is your whole R3. Okay, so you have to note it here that the dimension of V is the number of non-zero rows in the echelon form. Okay, if you will check it, here the echelon form of this, okay, so it will be the number of it. You will check the rank is equal to 3, that is the dimension. So the dimension of V is equal to number of non-zero rows in echelon form. Okay, for art. So for example, you will face the question that find the dimension of the vectors B is given that 1 0 2 2 0 1 and 1 0 1. They are asking you what is the dimension. So actually I want to note it here that the dimension of this vector space is actually dimension of the linear span of this B. Okay, for example here the dimension of this will be the dimension of the linear span, and you can check it is linearly independent. Dimension is 3, the rank is 3, so that means dimension is 3, the number of non-zero rows. So from this what you can do, you can make a matrix here. A is equal to 102, okay, 201, 101. Okay, now you can create an echelon form. So on apply R2, so sorry, R3, R3 gives you R3 minus 2 times R1, so it will, you will get 1 2 1, so it is 0 0, sorry, it is 102 201 101. Okay, so you will get 0 0 0, and 2 minus 2 is 0, 1 minus 2, that is minus 3, and 1 minus 2 is minus 1. And in the echelon form you have to keep the row as at the bottom, so it is 1 2 1, 0 minus 3 minus 1, 0 0 0. So this is a pivot element, this is a pivot element, so number of non-zero rows is equal to 2. It means the dimension of your basis, that is the linear span of dimension of linear span of your B will be equal to 2. Okay, is this clear? Is this clear? Okay, let's go forward. So for example, the question will be like this. Okay, the question, they may ask you the question that prove that the vector v1 is equal to 1 1 1, v2 is equal to 1 1 0, v3 is equal to 1 0 0. These are the three vectors. You prove that this is the basis for the R3 over R. Also prove that the vector, for example, they will give the vector v is equal to 1 3 1, okay, can replace any one of the three. Okay, so this 1 3 1 can replace any one of the three vector of the basis to form a new basis. For example, what I am telling you. So you have given vector v1 v2 v3. First check that whether it is a basis or not. So for that you have to create a matrix. You can create a matrix A, and you can create the column here. So v1 alpha 1, v2 alpha 2, v3 alpha 3 is a linear span, so you can create a matrix in this way: 1 1 1 1 1 0, is it, and 1 0 0, is it, in this way. So you have 1 1 1 1 1 0 1 0 0. Even by the echelon form you can do it: 1 1 1, 1 minus 1 is 0, 1 minus 1 is 0, it is minus 1, 1 minus 1 is 0, it is minus 1, and it is minus 1. So you can write it in this form: 1 1 1, 0 minus 1 minus 1, and 0 0 minus 1. These are the pivot elements, and you have seen the rank of A is nothing, that is 3. So it means it is linearly independent, the number of unknowns, because alpha 1 v1, alpha 2 v2, alpha 3 everything, it is linearly independent. So it means that v1 v2 v3 are linearly independent. Now we will check the span. So as let's say B is equal to your v1, your v2, your v3, and the linear span of B will be alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, and these alpha are the real numbers. So what will you do here? Now the alpha 1 v1, you have the v1 as 1 1 1, so alpha 1 1 1 1 plus alpha 2, your v2 is nothing, 1 1 0 1 1 0, plus alpha 3 is nothing, 1 0 0, as alpha are the real numbers. So what will you get? You will get alpha 1 plus alpha 2 plus alpha 3 comma alpha 1 plus alpha 2 comma alpha 3. Okay, and alpha I are from the real number. As you have seen, these coefficients are the linearly independent, so every these vectors will be different. So it means that it spans, so this is different, this is different, this is different, so every real number can be written in this linear combination. So alpha 1 alpha 2 alpha 3, so it means that the dimension, so it will be your R3, is it? So it means that the dimension of linear span of B is equal to the dimension of your R3 is equal to 3, it means that B is the basis. B is the basis of R3. Okay. Now, as I told you, you have to show 1, 3, 1. Okay. Now, you have 1, 3, 1. Okay. So, as I told you, you have to prove that the vector 1, 3, 1 can replace any one of the three vectors of the basis to form a new basis. So, now you have 1, 3, 1 as, you can write it, 1, 3, 1 as alpha plus beta plus gamma. Okay. Another one is your, sorry, here alpha. So you have here elements 1, 3, 1 is the vector. So what I told you, that you have to check 1, 3, 1 is a vector in your R3. So it will be the linear combination of this. That means this will be there. So that means it will be in the linear combination. So 1, 3, 1 will be in some alpha 1 plus alpha 2 plus alpha 3 comma alpha 1 plus alpha 2 comma alpha 3. So it means that your alpha 3 is equal to 1. Okay, your alpha 3 is equal to 1. It means that your alpha 1 plus alpha 2 is equal to 3. Is it? This one. Alpha 1 plus alpha 2 is equal to 3. And also here alpha 1 plus alpha 2. So alpha 1 plus alpha 2 plus alpha 3 is equal to 1. So as this is 3, okay, this is 3, and or you can check it here, your alpha 2 will be 3 minus alpha 1. Okay, so put it here. So alpha 1 plus 3 minus alpha 1 plus alpha 3 is equal to 1. And your alpha 1 is, so alpha 1 plus, so it is 0. Okay, 0 alpha 1 plus 3. So it means that here what we have, okay, so we have alpha 1 plus alpha 2 plus alpha 3, alpha 1 plus alpha 2, and we have here alpha 1. Okay, sorry, it is alpha 1. Okay, it is alpha 1. So we have here mistake. So it is here alpha 1 actually, because you have alpha 1 here, you don't have here any element, here no element, so that is alpha 1. So it means that 1, 3, 1 will be equal to alpha 1 plus alpha 2 plus alpha 3, alpha 1 plus alpha 2 and alpha 1. So it means that alpha 1 is equal to 1. It means that alpha 1 plus alpha 2 is equal to 3. It means that alpha 2 is equal to 2. It means that alpha 1 plus alpha 2 plus alpha 3 is equal to 1. So that means alpha 1 is 1, alpha 2 is 2 plus alpha 3 is equal to 1. So alpha 3 you got that it is minus 2. Is it? So you got the alpha 1, you got the alpha 2, you got the alpha 3. So since these alpha, beta and alpha 1, alpha 2 and alpha 3 are the non-zero scalars, so 1, 3, 1 can replace any one of these three vectors. So that means this is a linear combination of this. So we find the alpha, beta, sorry, alpha 1, alpha 2, alpha 3 for the same vector. Okay. So similarly, for example, if it will be given that you have the vector, let's say alpha 1 is equal to 1, 1, 0, 0. Alpha 2 is another vector that is 0, 0, 1, 1. Your alpha 3 is given as 1, 0, 0, 4. These are given vectors. Even alpha 4 is given as 0, 0, 0 alpha. These all vectors are in the R4 over R. Okay, you have to check whether these are the bases or not. So for that, first check that it is linearly independent, make a matrix. So okay, keep all the vectors as a column, 1 1 0 0 0 0 1 1, and similarly 1 0 0 4 0 0 0, and it is 2. Okay, so 2. Okay, check the rank of a, so make it into the echelon form. So you will get 1 0 1 0, 1 minus 1 is 0, so 0 minus 0, it will be minus 1, it will be 0. So it is 0 1 0 0, so it is 0 minus 1 is 0, sorry, 1 minus 1 is 0, 4 is 4, that is 2. Okay, so you have here element, you have here any element. Okay, you can do it here. So it will be 0 0 1 0, it will be 0 1 0 0. Okay, and you have here 0 0 4 2. Okay, 4 times this plus this, so this will be 0 0. So this is minus 4 plus 4, it is 0. This is 4 times 0 plus 4, it will be 2. Okay, so now check your rank is 4, and you have how many vectors? You have the 4 vectors, means 4 unknowns you will find. So it means that it is linearly independent. It is linearly independent. The first condition hold. So the rank of A is equal to 4 is equal to number of unknowns which we will find in the linear span. It means linearly independent. Okay, or you can go through the determinant as well. Now check its linear span. So we can't say about the basis yet, so because we have to find the linear span. That's your A alpha 1 plus B alpha 2 plus C alpha 3 plus D alpha 4, and these A, B, C and D are the real numbers. So what will you get if you will multiply 1 1 0? So that is A 1 1 0, is it 1 1, sorry, 1 1 0, yes, 1 1 0 0. Okay, second is plus B, your alpha 2 is 0 0 1 1, and your alpha 3 is 1 0 0 4, and your alpha 4 is 0 0 0 2. Okay, so these A, B, C, D are the real numbers. So what will you get? You will get A plus C. Okay, A here, 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 nothing, and then B. Okay, then at the end B 4C, so B plus 4C plus 2D. So this is the A, B, C, D. This is the linear span. You can check already these are linearly independent, so you will get the unique solution for A, B, C, D. So here you can check that this one is the this has the dimension 4 because all are linearly independent. So it means that the dimension of linear span of S is equal to 4, that is the dimension of R4. It means that S is the basis. S is the basis. Even if you have to find whether it is linearly independent or not, so you have to check the coefficients or have the unique solution. So you can make a matrix here and check it, and you will find the unique solution, that is 0 0 0, all are A, or you can directly find it A plus C, A, B, B plus 4C plus 2D. This linear combination should be equal to 0 comma 0 comma 0 comma 0. So it means A should be equal to 0, B should be equal to 0. That means C will be also come to the 0 and D will also come to the 0. So that's linearly independent. So this is the basis. Similarly, you will find the questions like this. If V is given as 3 comma minus 5, so express this as a linear combination of the vectors. The vectors will be, let's say, S is equal to V1 is 1 comma 2, V2 is equal to minus 3 comma 1, So these are in the two dimensional. So if you have to express it, what will you do? So 3 comma minus 5, you have to write alpha 1 v1 plus alpha 2 v2. So your alpha 1 is alpha 1 1 comma 2 plus alpha 2 is alpha 2 minus 3 comma 1. So what will you do here? So that is alpha 1 minus 3 alpha 2 and 2 alpha 1 plus alpha 2, and it should be 3 comma minus 5. So you have the 2 alpha 1 minus 3 alpha 2 is equal to 3, and 2 alpha 1, okay, plus alpha 2 is equal to minus 5, and solve you will get the alpha 1 and alpha 2. That is the set that you will express this as a linear combination. This is only possible if this system has a solution, that is 1 minus 3 2 and 1 3 and minus 5. You can also go for this as an augmented matrix. If it has a solution, that means this we can write as a linear combination. Okay, so similarly there are many questions in this way. I want to note it that as we have discussed, the Pn over T or Pn over X is the set of all the polynomials whose degree is less than or equal to n. So similarly, the P3 of x is the set of all the polynomials whose degree is less or equal to 3. So its elements will be a0 plus a1x plus a2x squared plus a3x cube, and these coefficients are the real numbers. Now its basis, we have to remember, it is 1 x squared x cube. So that means the dimension of P3 of x is equal to 4. Okay, so every polynomial can be written as a linear combination of these polynomials. In general, the dimension of Pn of x is equal to n plus 1. So thank you very much. We will discuss the linear transformation in the next video. Thank you.